Okay, let's get started. Again, good morning and welcome to CAM Logic's edition of Tech Tuesday. My name is John Gaioni and I'm the Director of Marketing at CAM Logic. Joining me today and actually presenting is Brent Ross of Motionport. Motionport is our Siemens PLM business partner supporting us in FEMAP. Today's webinar is entitled Obtaining Useful Loads for Use in Structural Analysis, and the software we're talking about is FEMAP. Before I turn it over to Brent, I'd like to give you a little background on CAM Logic. CAM Logic is a leading provider of product life cycle solutions and 3D technologies that include scanning and 3D printing. These technologies help companies build better products, improve their processes, reduce costs, and maximize profitability. We provide unparalleled 3D engineering technological software solutions along with the services and support to ensure our clients' successes. We have over 16 years of CAD/CAM CAE expertise. We have world-class software partnerships, most notably with Siemens PLM, including NX, Teamcenter, the Velocity series, which includes Solid Edge, and of course FEMAP. We pride ourselves on our fervent focus in understanding our clients' processes, needs, methodologies, and unique challenges in order to provide you with real solutions and the technological edge in today's competitive environment. We strive to be your engineering technological partner. I look forward to that opportunity. Thank you again for joining us today. And now Brent will show us what's new with FEMAP here. Thank you.
Okay, thanks a lot. So I would first like to say that the focus of Motionport is in the computer-aided engineering area, looking at different types of analysis. So that includes structural analysis, motion simulation, control systems, and heat transfer topics. So we'll talk a little bit about the interaction of structural analysis and motion simulation because that's what this load topic is all about. So a previous webinar we gave about 2 months ago had to do with an overview of FEMAP and looked at the overall process with FEMAP. As you can see here on this box, you can go back and view that earlier webinar through the CAM Logic website as well as directly through YouTube going to user CAM Logic. In that earlier seminar, we talked about the overall process, starting out with the mesh creation, applying material properties. Next step was definition of constraints and load cases. So we have load cases highlighted because that's the focus of this particular webinar. And then with FEMAP, you have the embedded NX solver used to run the analysis, and then you review and document results. So in this situation with loads, there are different type of loads. We'll talk about that. But loads are key to running this kind of structural analysis. And they're also the biggest input challenge because some aspects of the input to the model are very clear. So things like the geometry of the component, you can obtain that from your CAD. And it's very clear what that geometry is. And then things like constraints, you can identify where your product or your component is constrained, and that's kind of an on or off type of condition. You know, the particular area is constrained or it's not constrained. But loads and material properties are well known. You can look up all those properties. But the loads have to do with how the system is operating, and the system can be operating at different speeds under different conditions, and then the question is, okay, what kind of loads are being imposed upon the components based upon what's happening during the work cycle? And sometimes that can be readily obtained with some kind of instrumentation, but sometimes it's hard to instrument areas of interest where loading is occurring, especially if the load is some kind of contact, sliding contact, and so it's hard to put instrumentation in that area. Okay, so how might loads be defined? There's a variety of categories. First one is static or dynamic loads, and we'll talk about each of these areas shortly. The second area has to do with the load distribution. Are the loads applied at a sort of a given local area at a point, or is it some kind of pressure distribution over a surface? Another category to look at with loads, it would be, are you looking at a single point in time with a certain load case, or are you looking at a time history with many different load cases that are distributed together with some sort of time interval? So we'll talk about each one of these areas. So static versus dynamic loads. A static load is looking at a system in equilibrium. So if there's no significant motion, the forces that are being applied to the system would be things like gravity. You could have springs in the system applying a steady load. You could have other types of external forces, but the idea is that these are steady loads, so it's a steady loading condition or a static loading condition. And then the other type of load is a dynamic load. And so some characteristics of dynamic loads have to do with the system having an impact occurring, or there might be acceleration in the machinery, or even just if there's just steady rotational velocity, but maybe an imbalance of what's being rotated, that can cause some kind of a pulsing load according to the rotational speed of the system. So when you think about dynamic loads, there's going to be some kind of motion involved in the system, and the dynamic loads are going to tend to be higher than the static loads. So when everything is steady in a product, that's going to be a lower set of loads. The dynamic loads are going to reflect higher loads. So when you want to design your components to have a correct product life, the durability considerations, make sure things won't break, things won't fail over time, it's really important to keep in mind the dynamic loads that are going to occur in your systems. They're a little bit harder to obtain, but they're going to be the loads that really affect the product life. Okay, point loads and pressure loads. Here in the upper right, we see this simple diagram out of a textbook where you have a beam and you're just loading it. You have a single pressure load, or not a pressure load, you have a point load at a given location along the beam. That load could be applied anywhere along that beam, but the idea is that it's local where it's applied. And then contrasting that, a pressure load might be distributed over an entire area, as shown here in the lower right. This particular component has reinforcing beams where you see more of the blue-green colors, and then in between that set of beams making the arc, you have some thinner shell elements or thinner cross-section there, so that's why the response to the pressure load here is different. This is actually showing the stresses in the system. So the idea is that depending on what's happening with the system, you can have either type of load. If you have one component acting on another, that may be at a point, like at a joint. Loads like different fluid type pressures, hydraulic pressures, wind pressures for a structure. Any of those things can be pressure loads, which are then distributed. And the distribution can be defined as an even distribution, or you can define some sort of function, or you can just input like a spreadsheet worth of data to define that pressure load. Now the point load, when we look at applying this in FEMAP over a mesh, the idea of a point load is that if you apply a load at a single node in the structure, it's easy for that to produce results that are just not correct numerically, because typically what you'll want to do is distribute that load that's at a point, you still want to distribute it over a number of nodes locally in that vicinity. And that actually can become quite a natural thing to do, because if you think about a connection between components where you might have that concentrated load occurring at the joint, usually in that location you have some kind of hole, where there's a pin, and then kind of a collar. So the actual force is being distributed around the circumference of the hole. And so with FEMAP, you can use a rigid element where you apply that value for the concentrated load at a master node in the middle of the hole, and then have rigid, basically spokes coming out to the exterior circumference of the hole, and then thereby distributing the load over those nodes. And that's a kind of a best practice for doing that kind of loading. Okay, in FEMAP, there's support for data surfaces. And so all these loads that we've just been discussing, there are this notion of data surfaces to make it convenient and efficient to be able to input these loads and apply them properly. And this notion of data translation errors is an important concept, and the idea is that with the software we want to have the proper interfacing so that we can input the information, review it, and make sure that we haven't introduced any errors. So this is showing some examples. For example, you may do a computational fluid dynamics run. This would be an advanced application here, but the output of a CFD run, would be one of these pressure loads applied over a surface. And so you'd want to be able to pull in that pressure information and map it to the mesh, and then run the structural analysis and maybe introduce some other loads in the system in order to determine the stresses. So, we talked about the distribution of a pressure. So this is, talking about there can be one-dimensional, two-dimensional, three-dimensional spatial variation on what those pressures are, and FEMAP will be able to accommodate that very well. Okay, another variation here on the different types of loads is you can have a single load case at a certain moment in time, or you can have a time history that might cover a work cycle. And so the reason to do an analysis with a time history of loads is that you may have a situation where the forces in the system actually have to do with things like the inertial forces, and kind of tracking changing conditions on the component. And the other thing would be if you have a load case or a set of loads from analyzing a work cycle, and you want to review all the stresses throughout the work cycle just to make sure that you're identifying what are the key stress conditions of interest that might be used in durability. So there's two variations here. I think I would suggest for best practices is that when you have a system that goes through some kind of duty cycle or work cycle, it probably is a good idea to look at more than one load case. And you can do that by doing a sequence of these single load cases. In other words, you can set up the mesh and all the boundary conditions and so forth, and then just introduce a number of discrete single load cases. And you may be able to determine that by looking at plots of the loads and picking out some of the peak values. So then to maybe look at a half a dozen different load cases or whatever is appropriate for the work cycle that's being looked at, that can be done. And again, FEMAP supports that, the setup of all the load cases so that you're actually running one simulation, but then you have a whole set of outputs to review for the different load cases. So that's a very efficient process. The time history run is generally done with the explicit solver Nastran, so that looking at more of a continuous process of walking through all the different frames in time of the different loading conditions. So that's two ways to look at the loads from a time point of view. Okay, so what I would like to do at this point is I am going to hopefully bring another window on the screen. So I hope that's showing up. Okay, and this happens to be the RecurDyn software. So this is a package for simulating the dynamics of the system. So let me just play this back. And what we're looking at is a small tracked robot. And we're looking at the work cycle or the duty cycle here as climbing the set of stairs. Okay, so as we observe, this animation, let me come back to play it again here, we see that we're getting this dynamic loads from the point of view of, you can see that there's some motion up and down as it's going up the stairs, and that's a function of the contact with the various edges and the flexibility in the system, so that when it's hitting these stairs, the edges, you can see it's making contact just with the edges of the stairs, and so the system is bouncing because of all this changing contact and so forth. So if you were to plot the forces on components in this product, then you would also see the variation in the loads over time. Okay, so you can imagine, and that this initial impact here of the front track sets when it hits the first set of stairs, that might be one of the most severe impacts that occur during the simulation, is kind of just making that transition. So the other thing that we can see on this study is that as the robot gets up on the stairs, the track assemblies on the front are rotated down to provide a longer, effective, wheelbase going up the stairs for stability. But those assemblies are first rotated up because it needs to be up to climb up on the stairs, and then I can see it straightening back down here. So when you look at the load conditions, the other aspect is, as certain parts of assemblies of interest, as you have different motions occurring, again, that can impose some of the higher loads. So the idea is to use a product, whether it's RecurDyn or whether it's like NX Motion, can also do these kinds of motion simulations and calculating force. These are ways to use simulation in order to obtain the load data that you might want to use to look at different components. And as you study the load data on the system, that also helps you identify which components deserve more attention. Because the components that are seeing the higher loads probably should be looked at, rather than the components getting lower levels of loading, given that they're maybe made of the same material. So this is, kind of the sequence, is that with FEMAP, you need to have accurate loads in order to get accurate outputs. And in order to get accurate loads, you can use this kind of simulation, or you can obtain data from tests. But from a best practice point of view, the recommended way is actually to use both simulation and test. Okay, so in other words, when you have a product like this, and maybe it only exists at the very beginning as a concept, okay, then that would be your only source of estimated loads, would be from the simulation. But then as you build the first prototype, then you want to check loads being generated from the prototype compared to the loads from the simulation, and make sure that those loads are matching. And an important aspect is that there's a cost to measuring loads experimentally, and as I mentioned earlier, some loads are not readily measured experimentally. So the best practice is to say, do a simulation like this, compare it to physical results once you have a physical prototype or an actual product to test, and obtain, get the physical results for the load data that you can obtain readily from the testing and from the instrumentation, and make sure that that's all matching. And if you have a model that's matching those measured loads, then for areas that's really hard to measure, then you have some good confidence to use the loads from the simulation. And then as time goes on, as you continue to work with a given product line, the idea is to always use the physical prototype to continuously, or the physical product, and do physical testing on an ongoing basis, continue to help improve the quality of the system model. And then as you go on to develop new variations of the product, then your simulation techniques will be accurate enough to really be able to do some predictive work with regards to loads and to have a good amount of confidence. Okay, so that's kind of the philosophy of how to get a good system for getting the right loads to then import into FEMAP in order to do the component analysis. Okay, so based upon this review we've had, the action item for you is really to say, what is your plan to obtain and use load information more effectively? So that has to do with identifying, which are the important loads on a given component, and you need to identify those loads so that you make sure that both from a simulation point of view as well as from a physical test point of view, that you're aware of where you want to obtain loads so that you can make sure that the simulations and the test setup will obtain loads in the important areas. Second is that you want to obtain accurate loads, and as I mentioned, this is really a combination of using physical test and simulation, and to compare the two of them. That's when you know that you have high confidence in the loads. And it is possible for there to be errors both from a simulation point of view or from a test measurement point of view. I mean, test equipment can fail or give poor readings due to some issue that may go on. It is possible to not get good results from the simulation if the model doesn't include all the important aspects. So if you use these two things together, the physical test and the simulation, once you start getting agreement between the two, then you can really have good confidence there, because the types of sources of error for the two different types of techniques are different. So the idea is that once you get things to match, that means they both must be giving correct answers. And then once you obtain those accurate loads, then it's a matter of using these loads well in FEMAP to make sure that you're defining loads using best practices so that the loads are being distributed properly through the structure. And then as you do a thorough case, you are going to have lots of results, so you want to be able to classify, store those results so that you have good access to them, and also develop good techniques for reporting the results. And that's going to really vary with each organization and each product, but the idea is that you should develop your own templates for reporting results and certain techniques that are consistent so that people can understand it well. So with this process, again, we've mentioned that we have the software, through the combination of CAM Logic and Motionport. We provide software and support to use the software to support this use of loads in order to do the proper component analysis. So that's the end of today's seminar. We're about out of time, so we just wanted to close out by making a few comments that the webinar can be found for replay on YouTube and generally posted within 24 hours from now. This one should be, and there are past webinars. So earlier I mentioned about the earlier FEMAP seminar that went through the basics of the process of deploying FEMAP for evaluating the performance of the components. So this information is available through the CAM Logic website, so camlogic.com, or you can go onto YouTube/user/CAM Logic and also be able to see a list of the available webinars. So again, as John said, thanks for joining us in this webinar. Here's some contact information, both for CAM Logic and with FEMAP. Technical support through Motionport is available to you. So thanks again for attending, and hope everyone has a great day.